the silent equation behind every tipping point. Nothing dramatic announces a tipping point. No alarms, no countdown, just a quiet shift that changes everything. To understand why tipping points feel sudden, we need to look at what actually drives them. Tipping points are not caused by large events. They are caused by accumulation. Pressure builds, connections tighten, and resilience drains long before anything visible changes. The transformation happens beneath the surface, in relationships between components rather than in the components themselves. Forces that once canceled out begin amplifying each other. Feedback loops that stabilize begin destabilizing. The mathematics governing system behavior remains consistent, but the parameters within those equations drift into dangerous ranges. This drift is gradual, continuous, and almost entirely invisible to casual observation. Only by tracking the right variables over sufficient time does the pattern emerge. By the time human intuition recognizes danger, the system has often already passed a point where simple interventions could reverse the trajectory. This matters because tipping points appear across very different systems. Climate patterns, social movements, financial markets, and even personal burnout all follow similar mathematical behavior. The surface details change, but the structure underneath remains the same. A forest ecosystem approaching collapse exhibits the same mathematical signatures as a financial institution approaching insolvency. The variables differ wildly, but the relationships between variables follow identical patterns. This universality is not coincidental. It reflects fundamental properties of complex systems operating near critical thresholds. Understanding these mathematical commonalities allows knowledge from one domain to inform understanding of another. The insights gained from studying ecological tipping points apply directly to economic ones. The lessons learned from social phase transitions illuminate organizational breakdowns. This cross-domain applicability makes the mathematics of tipping points among the most powerful tools for understanding system vulnerability. At first, systems absorb stress easily. Disturbances fade. Recovery is fast. Each challenge strengthens confidence that the system is robust. But with every absorbed shock, internal flexibility decreases. Margins thin. Response is slow. The system is not actually strengthening through these experiences. It is adapting in ways that specialize it for handling the specific stresses it has encountered, while simultaneously losing its capacity to handle novel stresses. This trade-off is invisible during the adaptation process, because the system appears to be improving. It recovers faster from familiar disturbances, responds more efficiently to expected challenges, operates with less waste under normal conditions. But this optimization comes at the cost of generalized resilience. The system becomes excellent at operating within a narrow range of conditions and increasingly brittle outside that range. What makes tipping points dangerous is invisibility. The equation governing the system does not change. The rules remain valid. Only the parameters shift. And those shifts are rarely noticed because outcomes still look normal. Performance metrics stay within acceptable bounds. Outputs meet expectations. Stakeholders remain satisfied. All the traditional indicators of system health continue signaling normalcy even as the system's fundamental character transforms. This creates a profound disconnect between perception and reality. Observers watching outputs see stability. Mathematicians watching parameters see impending catastrophe. The divergence between these views grows wider as the tipping point approaches, with confidence and stability peaking precisely when vulnerability reaches its maximum. This timing is not accidental. The same processes that drive the system toward its tipping point also mask the approach until very late in the trajectory. As the system approaches its tipping point, it becomes increasingly sensitive. Small inputs produce larger effects. Recovery takes longer. Variability changes character. These are not failures. They are signals. The system is broadcasting its changing state through these alterations in behavior. But the broadcast is in a language most observers do not speak. Standard monitoring focuses on whether outputs remain acceptable, not on how the relationship between inputs and outputs is evolving. A system can continue producing normal results while the effort required to maintain those results escalates dramatically. This escalation in effort reflects declining resilience. The system is working harder because it is becoming weaker, but this weakness remains hidden behind continued performance. Only by examining response characteristics rather than output levels does the deterioration become visible. But signals are often mistaken for noise. Efficiency hides vulnerability, and by the time the shift becomes obvious, the system has already crossed a line where return is easy. Tipping points are not moments, they are conditions. And mathematics is the only language that reveals when those conditions are quietly being met. As a system nears its tipping point, the silent equation begins changing how responses unfold. Disturbances linger longer than they used to. Corrections feel sluggish. What once bounced back now hesitates, then overshoots. This behavior is measurable. Recovery time stretches. Variance grows uneven. Extremes become more common. The system still appears functional, but it is working harder to stay that way. Effort increases while resilience declines. Control systems that once required minimal intervention now demand constant adjustment. Operators who once supervised passively now intervene continuously. The workload for maintaining stability grows, while the stability being maintained becomes progressively more fragile. This combination of increasing effort and decreasing effectiveness is characteristic of systems approaching tipping points, yet is often interpreted as temporary difficulty rather than structural transformation. At the same time, interactions tighten. Components that once behaved independently start moving together. Diversity collapses into alignment. This feels efficient. Coordination improves. The system looks unified and strong. Management celebrates the improved coherence. Metrics show reduced internal conflict. Decision-making becomes faster as consensus emerges more easily. The reduction in internal diversity is framed as organizational maturity, as the system learning to work together more effectively. But mathematically, this unity is a warning. When everything moves together, nothing can counterbalance failure. One shock now affects all parts at once. The system has lost its internal shock absorbers. The independence that once allowed different components to respond differently to different conditions has been replaced by coordinated movement that ensures all components respond identically. This coordination, while appearing beneficial under stable conditions, guarantees synchronized failure under stress. What makes this phase deceptive is success. Output may remain high. Metrics may improve. Stability appears earned. The silent equation hides vulnerability behind performance. The system may actually be achieving its best historical results precisely as it approaches catastrophic failure. This inverse relationship between performance and resilience is one of the cruelest aspects of tipping point dynamics. It means that the times when systems appear strongest are often the times when they are most vulnerable. Leaders reviewing excellent quarterly results have no indication that those results are being achieved through unsustainable practices that are eroding long-term viability. Investors seeing strong returns have no warning that those returns are being generated by taking hidden risks that will eventually materialize catastrophically. The success itself becomes part of the mechanism driving the system toward its tipping point. Observers often misread these signals. Slow recovery is blamed on temporary conditions. Increased variability is dismissed as noise. Synchronization is celebrated as optimization. Each warning sign is rationalized away individually without recognizing that they form a coherent pattern when viewed together. The human tendency to seek local explanations for each phenomenon prevents recognition of the systemic transformation occurring across all phenomena simultaneously. This fragmentation of perception is reinforced by organizational structure. Different departments monitor different metrics. Different specialists analyze different aspects. No one has responsibility for tracking the collective pattern. The holistic view necessary to recognize approaching tipping points exists nowhere in the institutional architecture. By the time information from disparate sources is integrated sufficiently to reveal the pattern, the opportunity for preventive action has usually passed. But the math sees something else. It sees a system approaching a boundary where small causes create irreversible effects, a place where return paths narrow, and once crossed, no amount of force can restore the old balance. The conflict emerges when the tipping point is close enough that action still matters, but certainty does not yet exist. The system feels stable enough to delay change, even as the math shows growing danger. This is an emotional peak. Decision-makers sense risk, but cannot justify disruption. Acting early looks extreme. Waiting feels reasonable. And so, hesitation becomes policy. The institutional machinery designed for deliberation and consensus becomes an anchor preventing the rapid response that mathematical indicators suggest is necessary. Committees convene. Studies are commissioned. More data is requested. Each delay is individually justifiable, but collectively they consume the window during which intervention remains possible. The organizational processes that normally ensure careful decision-making become obstacles to timely action. By the time consensus emerges around the need to act, the conditions have often shifted to a regime where action is no longer effective. Mathematically, this is the most fragile moment. Small interventions could restore flexibility. Minor adjustments could reopen return paths. But delay hardens conditions. Each cycle without action tightens coupling and drains resilience further. The opportunity cost of inaction compounds exponentially. What could have been accomplished with minimal effort early on requires massive effort later, then becomes impossible regardless of effort. This progression is deterministic once the warning signals appear, making early hesitation equivalent to choosing eventual catastrophe. Yet the institutional and psychological barriers to early action remain formidable. The problem is not lack of knowledge, but inability to translate knowledge into action when action feels premature. Systems designed to prevent hasty mistakes simultaneously prevent timely responses. The safeguards against overreaction become vulnerabilities, enabling underreaction. What makes this conflict so persistent is ambiguity. The equation does not predict collapse with a date or a headline. It only shows rising sensitivity. Without a clear trigger, warnings compete with habit, optimism, and short-term reward. Human psychology demands narratives with clear causes and definite timelines. Mathematical models provide neither. They offer probabilities and sensitivities, concepts that do not trigger the emotional responses needed to overcome institutional inertia. The abstract nature of mathematical warning competes poorly against concrete pressures to maintain current operations. Stakeholders want evidence of specific threats, not general indicators of increasing vulnerability. Without that specificity, the warnings are easily dismissed as theoretical concerns that may never materialize. This dismissal is psychologically comfortable and organizationally convenient, making it the default response despite its mathematical irrationality. As time passes, the system crosses a subtle boundary. Recovery paths vanish. Interventions that once would have helped now provoke instability. Control arrives too late and with too much force. The system has entered a regime where attempting to restore previous operating conditions triggers the very collapse that restoration was meant to prevent. This phase represents true irreversibility. The tipping point has been passed. The system cannot return to its previous state through any available intervention. It must either find a new stable state or complete its collapse. This irreversibility is often unrecognized initially. Operators continue attempting corrections that worked previously, not realizing those corrections are now counterproductive. The institutional memory of successful past interventions becomes a liability, driving actions that accelerate rather than prevent breakdown. The conflict is not ignorance versus knowledge. It is urgency versus comfort, and comfort is mathematically expensive. By the time collapse feels obvious, the tipping point is already behind you. The resolution comes when tipping points are no longer treated as surprises, but as outcomes of measurable conditions. Mathematics does not prevent collapse by predicting events. It prevents collapse by revealing when systems are losing the ability to recover. This shift in perspective is fundamental. It means accepting that perfect prediction is impossible while recognizing that useful warning is achievable. The goal is not to know exactly when or how collapse will occur, but to know when the system has entered a state where collapse becomes increasingly likely across a range of potential triggers. This knowledge is sufficient to justify preventive action, even though it cannot specify which specific trigger will ultimately prove critical. The uncertainty about details does not negate the certainty about increasing vulnerability. This changes how responsibility is understood. Action is taken when resilience declines, not when failure becomes visible. Flexibility is restored early, Diversity is protected. Stress is released instead of stored. These practices require accepting short-term costs to prevent long-term catastrophes. They mean maintaining capacities that may never be needed, preserving redundancies that appear wasteful under normal conditions, tolerating inefficiencies that optimization would eliminate. The economic logic that drives toward maximum efficiency must be balanced against resilience logic that preserves margins for error. This balance cannot be achieved through traditional cost-benefit analysis because the benefits of resilience are hypothetical and difficult to quantify, while the costs are concrete and immediate. Making resilient choices requires valuing avoided catastrophes as highly as achieved efficiencies, despite the asymmetry in visibility and measurability. The silent equation never demanded certainty. It demanded attention. Attention to recovery time, to rising sensitivity, to the narrowing of return paths. Systems that survive do not wait for proof. They act when the math says the window is closing. They accept discomfort early to avoid catastrophe later. Every tipping point is quiet until it isn't. The noise comes after the transition. The warning comes before it. Learning to listen to that warning is not prediction. It is wisdom. Subscribe to join the journey. The silent